Progress.
Unit 2 about based on the quantum physics and atomic and quantum physics. Both are in unit 2. More theories and more explanation here. Uh, then our aim is not face the CAT 2 and final exam and take the results. This is very useful to the higher studies, right? In level 5, nuclear and particle physics based on this quantum physics. And also, can you hear me?
Yes, madam.
Okay. Then, and also if you are doing special degree, master degree, then basic is here, right? So then you can read the course material careful. Then I will explain everything. But some theories and more descriptions are here. So then it's up to you. Then I can cover everything into exams and additional information you can get the course material by searching, right? This is very interesting subject. It is very useful for your higher studies, right? And you can do some experiment like this, right? Okay, shall we start in quantum physics? The first session one, it is in particles and waves. Particles and you know about the particles and you hear about the waves in physics and optics, you related with the waves. But in the quantum physics, the behavior of wave as particles and particle as waves. We can see in the quantum physics, we can explain the we call this as the wave particle duality. Wave particle duality, it means the behavior of waves as particles. Sometimes in some experiment and some theories, we can see the waves behave as the particles. And some can see particles as particle behaves as waves in some certain circumstance. Then in the quantum physics. So we call this as the wave particle duality. In first session, the explanation here, the wave particle duality, this one, right? It means the behavior of waves as particles and particles as waves under some certain circumstance is known as wave particle duality and together with special relativity. Then it provides an important contribution for understanding modern physics, right? Modern physics is based on the special relativity and other quantum physics and also atomic physics, right? Atomic physics and quantum physics are included in unit 2. In basic idea, you can get in. Then first thing is we have to understand what is the wave particle duality. Not like the classical mechanics. In classical mechanics, we saw the particles and waves. Separately we know, right? These titles, separately we know particles and waves, right? In the mechanics part, in mechanical part, we studies about the particles and optics of waves, then we study about the waves, right? They are independent in the classical mechanics part, right? They are independent, not they are both entitled both together. No, they are independent. Optics part and classical mechanics part, mechanics uh, are independent. These are the classical theory of particles and waves. But in the quantum physics, we study these are dual nature of particles and waves. Sometimes we can see waves behaves as particles and particles behave as waves, right? This is the thing in the modern physics, quantum physics, right? Individually we studied in classical theory, optics and mechanics about particles and waves separately. So in classical theories, they are independent each other, independent two disciplines here, right? In we considering electromagnetic some waves, you know about the electromagnetic waves. Then waves as waves when they exhibit interference. You heard about interference, diffraction, and polarization phenomena. These are electromagnetic waves behave as the waves, right? In this session, these are some experiments, photoelectric effect, quantum effect. These are called then waves behave as particles. So particles behave as waves. Then you can see, right? Okay, this is the introduction. Um, First part belong to the dual nature of electromagnetic radiation. Some Maxwell's equations can see dual nature of the uh, waves and particles, right? Then electromagnetic radiation we can categorize with several frequencies. You know that you heard the and you see then electromagnetic spectra. You can see then in this spectra we can see several types of waves according to their frequency or according to their wavelength, right? Then X-ray, gamma rays, microwaves, infrared, visible range. These are all belongs to the electromagnetic spectrum according to their frequency or according to their wavelength, right? In classical properties, I explained here, electromagnetic radiation also exhibits some particle characters, right? This concept was proposed by Albert Einstein, right? About the wave particle duality, right? And also in Planck explained the quantization of energy. In next slide, we can discuss about the Planck's explanation. These are quantization of energy, the wave packets. Then I will explain later. That then no, then they are uh, electromagnetic radiation acts like a stream of particle. We call this particle as photons. I think you remember the last in unit 1. We study about the photons. In energy equations, we study about the photons. So electromagnetic radiation, its propagate, then could be equally well of wave, non-frequency and wavelength, and particle has energy and momentum, right? And then this concept of dual nature, wave and particle, nature of the electromagnetic radiation. And we can introduce photon or then already you heard about the photons. Photons means packet of energy. Packet of energy, or we call this as quanta. They contribute largely for the birth of quantum mechanics. Birth of quantum mechanics based on the photons and EM radiations and things, right? In the black body radiation, we discuss this and go to the one. I think before we are going to the black body radiation, we can see. Okay, next video is right. Then we will go to the black body radiation. Then black body radiation means this is the black body. It's a small hole. You can see in this figure the opening cavity here. Then these are the good approximation for the black body. The hole or cavity you can see. This hole acts as the perfect absorber. Then good approximation of the black body is a small hole or this cavity, right? The nature of the radiation leaving the cavity through the hole depends only on the temperature of the cavity, right? Then all bodies emitted thermal radiations to their surrounding and absorb some radiation from them. Then all bodies, we know, then all bodies emit the thermal radiation, they can release their thermal radiation to the surrounding. And also, they can absorb this such a radiation from the environment, from the surrounding, right? Then if the body is at higher temperature than its surrounding, then what happens? It will cool over because its rate of emitting energy is higher than the rate of absorbing energy. Okay. When the two rates become equal, we call this is become as the thermal equilibrium. These are the non-information. Thermal equilibrium you heard. Then sometimes still I am not moving slide. Okay. It is in the black body approximation, right? I will explain something. So then there are bodies whose surface or thermal radiation incident upon then and therefore then they can absorb all the radiations incident upon their body. This type of um, bodies we call as black bodies, right? Then such black bodies do not reflect light and appear black at low enough temperature, right? Then this is the one most important, most example. Then this is the one example. This is good approximation for the black body. Then the small hole leading to the inside this object, right? Now slide is moving. In the black body experiment, then these are some this is not the chapter 2 image. The total power of the emitted radiation increase with temperature in the black body experimental results. You can see page number 6 about the black body results. We can take the Wien's displacement law here, right? You have to read carefully about 4 and 5 uh, pages. Then we can take the total. Then you can see some one graph here. Then black body experimental results. Then the total power of emitted radiation increase with temperature. We call this law as the Stefan law. Then this is the P is the power of emitted radiation and sigma a to the power E T4. Then you can see the sigma T4 is okay. E not need to the exponential one. This is the emissivity for the black body radiation. It's equal 1. So in your book, page number 6, in equation 1.2, it is okay. RT means the power of emitted radiation. Here you can see P, sigma T4 is okay. Here, these are the Stefan law. This is given for the, you can see M minus 2, K minus 4, right? Then it means for the per area, right? Then emissivity is E is equal 1 for the black body. Then 1.2 equation, okay. If you want to find the total power of the emitted radiation, you can calculate RT equals sigma T4. We heard then, I think you know, in the A-level classes or something, I think, we studied then radiations. Total power is proportional to T to the power 4. Kelvin temperature for power. Right? This is the Stefan law. Then RT is equal sigma T4. The Stefan law. Then this is the one results about the experiment, black body experiment. Then emitted radiation increase with temperature. This is the black body experimental results. Then we can take RT is equal sigma T4. Then emission
Excuse me, madam.
radiation power of, yeah.
Excuse me, madam.
Yes.
What is referred for capital A?
Capital A replace here area. Then we can divide this by A. Then in your book, RT is equal sigma T4. It is mean per area, per square root. Right? Per area.
Okay.
Then we can divide this by A. Then it becomes the equation 1.2. Is the emissivity. Then it is equal 1 for the black body. Then equation reduced to page number 6, 1.2 RT equals sigma T4. Right? If they are giving area, you have to multiply this by A. Right? And other experimental results in you can see page number 6, one graph here. And this is the peak of the wavelength distribution shift to short wavelength as temperature increase. In this graph, page number 6, in graph, you can see the maximum wavelength or peak of the wavelength. Then first line in the bottom curve is correspond to the 1000 Kelvin, and other curve 500 Kelvin, and other one is 200. Then you can compare the peak of the wavelength of these three distributions, and it is increase in temperature. Then 1000, 1500 and 2000, the temperature is increasing, but you can see peak of the wavelength. It is shifted which side? Shorter wavelength. Shifted shorter wavelength side, right? Shorter wavelength side, it shifted because then this line is corresponding to the frequency. Frequency increasing means lambda decreasing, right? So it is shifted shorter wavelength side when temperature is increases. This experiment results we called as Beam's displacement law. But in lambda max and temperature is equal 2.898, this is the constant value. And for all three curves, if we multiply lambda max into its Kelvin temperature, this constant is coming, right? We call this as the Beam's displacement law, right? Lambda max is proportional to T, 1 over T, and also the frequency maximum value proportional to T. You can see the frequency line, frequency increasing, lambda decreasing. So, peak of the wavelength distribution shifted to shorter wavelength as temperature increases. This is the Wien's displacement law, right? We can compare some bodies lambda or temperature using the Wien's displacement law, right? The intensity increases with increasing temperature. Can't you see this? The intensity of black body radiation, the intensity increases with increasing temperature. The amount of radiation emitted increases increasing temperature. Then according to the curve, we can take the area under the curve. The peak wavelength decreases with increasing temperature. We know it, right? Peak wavelength decreases with temperature increasing. These are the intensity related to the black body radiation. Then other theory we can take as the distribution functions in page number 7. You can see it can be vary because some constant here, if constant are equal for the one constant, then reduce the equation, right? This is the classical attempt of the explain black body. Rayleigh's law, we call this as Rayleigh's law. The yes, then page, it is equal to I lambda T means intensity. Intensity depend on lambda and T. It is equal this one. You can see others are constant. It is proportional to the 1 over lambda 4, right? And T. Right. Then in page number 8, you can see the experimental results and the classical theory. It can see in this figure. The shorter wavelength, there was a major disagreement between Rayleigh's experiment. It is mismatched with the classical theory. Then you can see red-brown line. It shows the classical theory and intensity growing without bound of short wavelength. This is in the experimental data. You can see blue curve, right? Intensity and wavelength. It is varying according to the blue curve in the according to the quantum theory. And other one is classical theory, right? This is the Rayleigh's experiment. Then you can prefer page number 6, 7, 8 in more information, and most then for your calculations and other things. Most important theory is Stefan law and the Wien's displacement law, right? Then you can explain Wien's displacement law in page number 6. These are the experimental results based on the black body experiment, right? Black body experiment based on the black body experiment. We can take Stefan law and Wien's displacement law. Okay. Yes. And the important things, then you can follow the Rayleigh Jeans experiment here. Then if we are giving some questions, we are give this equation also Rayleigh Jean equations. Right? No need to memorize it, but go to step by step and please understand, right? Because then this is very useful for your higher studies and level 5 nuclear and particle physics, right? Then we can move to the Planck hypothesis. It's Planck. Introduction to the concept of quantum of actions, right? It's the next Planck hypothesis we can see. Yes, I will explain. You can get more. Planck's theory can combine with the black body radiations, right? Then can you see the full screen? I think yes. Planck developed a theory of black body radiation that leads to an equation for the intensity of radiation. This equation is in complete agreement with experimental observation. Then he built a theory based on the experimental radiation experiment observation. Here. Then Planck assumed that cavity radiation came from atomic oscillation in the cavity walls. And Planck made two assumptions about the nature of the oscillator in the cavity walls. In some content solid state physics in level 5, you can study about these oscillators. And if atoms are in solids, we assumes that they are vibrating to each other. And just like the simple harmonic oscillation, it's just like a simple pendulum. One atom try to oscillate other one, then they are oscillator, right? In solid state physics, if you are doing the solid state physics, you can memorize that. What I am telling here. Then Planck made the two assumptions about the nature of this oscillation. Right? Atoms are moving to each other and we assume these are so showing simple harmonic oscillations, right? Then Planck assumed that the cavity, then black body radiation means we take black body one cavity. I think you remember this figure here. This is the good approximation of the black body. So Planck think then in this cavity, black body is showing oscillator, just like oscillating each other. Then Planck made two assumptions about the nature of oscillators in the cavity walls, right? Then I think you heard this one previously. The energy, then first assumption, right? Planck assumption, then first one. The energy of an oscillator can have only certain discrete values, En, right? En is equal NHF. We know this one. F means frequency, H mu. And what is the H? H is the constant, Planck constant, right? And N is the positive integer called quantum numbers, HF. En equal HF. These are very useful to study in hydrogen atom. We have to study it in the last sessions. So then En is equal NHF. H is Planck constant and F is the frequency of the oscillation. We call this as positive integer, just like 1, 2, 3, 4 like this. Then En equal HF. The energy of an oscillator can have only certain discrete values En. If then n is positive integer, if n is varying, sometimes n equal 1, what is the value? HF. We call this as the ground state energy or something, right? Then other one is if n equal to, then what happens? En become as 2HF. It is another level, right? And n equal 3, 3HF. It is greater than energy n equal to 1. It is above the n equal to 1, n equal 3. Right? Then we can get the idea. For the one state, they have one energy values, En. So the Planck says the energy of an oscillator can have only certain discrete value En. If here oscillator means then cavity, right? Cavity. Or then for the solid, we can take this as the oscillator because solid particles moving each other, they are showing simple harmonic oscillation. Act as the simple harmonic oscillator, then we can say the energy of the solid particle can have only certain discrete values E A, right? And this says energy is quantized. Energy is quantized. Then one packet of energy E N equal HF, then other one 2 HF. Two packets, two quantized, right? They say energy is quantized. Each discrete energy value corresponding to different quantum states. Yes. Then n equal 1 is one quantum state, other one is n equal 2, other one. So discrete energy value corresponding to the different quantum state, right? Each quantum state is represented by quantum number n. Quantum number can equal n equal 1, 2 like this. So we can see discrete energy values are corresponding to the different quantum states. This is the first assumption. I think you can understand, right? In the ground state energy, n equal hf equal 1, energy is hf. Then we are taking some energy, absorb some energy. Then if not black body, then if we are considering black body, because this is based on the black body radiation experiment results, then for the black bodies absorb some thermal energy, the EM theory then goes to the higher energy values. It is equal NEN equal 3HF like this, right? Okay. Then oscillator can have only certain discrete value EN, and we call this energy is quantized. Right. This is the other assumption. The oscillator emit to absorb energy when making a transition from one quantum state to another. We know about it, right? Then if this is it in the higher energy level, this can emit some energy and come to the ground state, can transition to another quantum state. If this is in the ground state, then this can absorb energy and can go to the higher state than this one. Can absorb and can go to higher quantum state. Right? Then this is the Planck's second assumption. The oscillators emit or absorb energy when making a transition from one quantum state to another. The entire energy difference between the initial and final state in the transition is emitted or absorbed as a single quantum of radiation. An oscillator emits or absorbs energy only when it changes quantum state. So, okay, then ground state, highest level, then highest level to ground level. So, changes the quantum state. The energy carried by the quantum radiation is E equal Hf, right? N is the integer, so energy is carried by Hf like this, right? This is the second assumption Planck made. Right, then you can see here. This is the second assumption and also the first dimension can see in this figure, right? The double arrow headed arrows indicate allow transition. These are the transition. 3 to 4 and 4 to 3 double line can see, right? An energy level diagram shows the quantized energy levels and allow transition. Energy is on vertical axis, right? You can see energy in this side, vertical axis. Horizontal lines represent the allowed energy levels. Then you can see in 0, 1 energy level. This is the ground state one, okay? And other one, 1. What is the energy? According to the Planck constant, HF. And the second one, 2 HF. And third one, 3 HF. And fourth one, 4 HF. Right? Then these are represent allowed energy levels. And double-headed arrows indicate the allowed transition. Then you can see some can happen. Take the energy HF, one photon energy, one photon and go to first excited state and second other one. third like this, and fourth. Then fourth steps can move third one, second one, by emitting radiations, emitting energy. And 0 to 1, you need to absorb energy, right? I think you can understand. This energy level diagram shows two Planck assumptions, right? Okay. Then the average energy of the wave is the average energy difference between levels of the oscillator weighted according to the probability of the wave being emitted. The weighting is described by the Boltzmann distribution law and gives the probability of state being occupied as being proportional to e to the power minus e kBt, where E is the energy of the state, right? This is Boltzmann distribution. You can meet in some higher levels. In level 6, statistical mechanics based on the Boltzmann distributions law. Then here the Planck modules, then this one describing the Boltzmann distribution law. It is the probability, but how to move in the stage being occupied, being proportional. It is proportional to pi minus e beta t. Just information, right? Don't worry about the Boltzmann distribution, right? Then this is also the Planck's modules combine the Boltzmann distributions law, right? For some graphs here. For the additional information you can see here, then wavelength and intensity. We know this is the, according to the Winslow-Spin law, this is the lambda max value, right? Okay. And at short wavelength, there is a large separations between energy levels. Then you can see here short wavelengths, right? And the long wavelength, there is a small separation, no? Then this side is short wavelength side. This is the wavelength axis. It is increasing with the x-axis positive directions. You can see in the initially short wavelength range. So there is a large separation with the current. Large separation between the energy levels leading a low probability of excited state and few demands transition. Right? The low probability of transition lead to the low intensity. Here then separation means then no transition is very small. Small means the probability is less value. Right? යාමේ හැකියාව කියන එක සම්භාවිතාව කියන probability is a less value because in the short wavelength large separation you can see, right? N equal to 1. But in the long wavelength there are the separation is very low, right? A small separation between the energy levels leading a high probability. The excited state can many downward transition. You can see here many downward transition can happen, right? The low energy in each transition lead to low intensity, right? Right. The Planck's wavelength distribution function, they all are in your book, right? Then wavelength distribution law, we can take lambda I lambda t, right? Theoretical expression for the wavelength distribution. The one expression, right? It is the Planck constant 6.626 into 10 minus 34. In the calculation, we are giving this one. And you remember the Rayleigh-Jeans equation and Rayleigh-Jeans 1. The long wavelength Planck equation reduced to the Rayleigh-Jeans expression. At the short wavelength, it predicts an exponential decrease in intensity with decreasing wavelength. Right? This is an agreement, the experimental results, right? Then in the Planck equation can reduce to Rayleigh-Jeans equation in the longer wavelength. But in the short wavelength, we can see exponentially decreasing in intensity with decreasing wavelength. These are the experimental results. We can take the Planck distribution. Then Einstein and Planck results. Then this is results by assuming oscillation of the electromagnetic field were themselves quantized. In other words, Einstein proposed that quantization is the fundamental properties of light and other electromagnetic radiation. So this led to the concept of photons. For electromagnetic radiation, it led to the concept of photons. Then can quantize, then can absorb photons, can emit in the photons, can see energy levels difference, and we call this as the quantization. It's the fundamental property of the light. and electromagnetic radiation. Right? Okay. Then before moving to this one, I think you can understand about the Planck's law and things. Uh, Please refer book session 1, very interesting, and you can get the more information. Now see example 1.1 in page number 3. It is related to the photon energy. Okay. You can see we can determine the frequency and wavelength of the photon of non-energy, right? In the photon energy, then best equation is equation is equal h nu. Then find the frequency and wavelength of the photon of energy is given 1 kilo electron volts, right? Then energy can measure by joule or electron volts, right? Then you can convert electron volts to the joule. 1 electron volt equal 1.6 into 10 minus 19 joule, right? For the calculation, we are giving all the things in your paper, right? Then here I want to say, you can see then photon energy. We can't find the photon energy as the kinetic energy half mv squared like this. Or we also discuss in the relativistic mechanics in unit 1, right? Then this example show that frequency and wavelength, how we find the frequency and wavelength for the non-energy of photon, right? Then given find frequency and wavelength of the photon of energy 1 kilo electric volt. 1 keV. Then we have to find the wavelength and the frequency. We can use the equation E equal hf, Planck equation. Frequency, h nu is also, right? Okay. H nu or hf. We can use the one. hf, then I'm using as if frequency. F is equal E over H. We can find the frequency here. Then first we have to convert this into joule, right? 1 into 1.6 into 10 minus 90 and also 1 into 10 3 because kilo electron volts, right? Then divide by Planck constant 6.63. We can take this as 6.63 into 10 minus 34 joule second. Right? In outside this is joule because you can see units. It is equal to seconds per second. Per seconds means hertz. Right? That's why we have to convert this one. Okay. So we can find F value. We use E equal HF value, Planck's equation, right? HF value. Then also we can find, if we are knowing F, how we find the lambda? What is the relationship lambda and nu? Lambda we can find as E equal H over F. We can replace this by Hc over lambda. These are the same equation. Same equation. F can be replaced C over lambda. If we have find the F, then we can find lambda. Nu is equal F equals C over lambda. Then you can find lambda value, right? This is the Planck equation. Okay. Right. See the second one. Then you can calculate and you can solve the equation. I want to explain about the Planck equation. In second one, this example show that how to determine the momentum for photon for the non-energy, right? Then for the equation for the momentum, P equal E over C. P equal E over C, right? Or last unit we discussed about this. Photon energy. Then they are giving momentum as 10 mega electron volts, MeV. Then we have to find the momentum of the photon, right? Then P equal 10 mega electron volts, 10 into 10, 6 mega electron volts, and also multiplied by 1.6 into 10 minus 19 joule and divided by C. C is the velocity of light, right? Then we can find momentum of the uh, this one, right? Okay. And look the last one, 1.3 also. The example show that how to calculate the number of photon emitted from the source of the non-frequency and power. The power is given and frequency in radio station operators at frequency 105. F is given as 5 megahertz. And with the power output, P is given, power is given as 250 kilowatt. 250 kilowatt. The energy then they are asking about rate of the emission of photons. Photons of this station. How many photons emit in the 1 second? The question is here, right? Then we can find frequency is given. We can find the energy of the one photon. The energy 1 packets of a photon. Photon can take as the energy packets, right? We can find the energy of one photon. It's equal h nu. All details are given here. Then you can find energy. And asking rate of emission of photons, we know rate of power is given. Rate of emission of photon, we have to find how many photons in here. Then number of photons for the time, right? R is equal number of photons divided by time. This is the photon, right? Not proton. Photon, energy packets, photons, right? Time, then we can take this as then output energy is given. Energy over time we know, right? We can take this as output energy can divide by energy of one photon. One photon. This is the number of photons we can take. Energy over energy of one photon and also time here. Then we can replace energy over time by power. Power can divide by energy of one photon. Energy of one photon. Then the answer is come, right? Energy of one photon, right? Then I want to, you're familiar with E equal H nu equation, right? Equal H nu. Okay? Right. Now we can move to the other session. It is one of the particle wave nature of the electromagnetic radiation. Can see for the example the photoelectric effect, right? So please follow this carefully. Then questions can give, right? Okay, go back to the PowerPoint. Right, Planck radiation, backward radiation, finish. No, photoelectric effect, right? I will discuss some questions and I will explain these some theories. So please follow carefully. Okay, please follow carefully. Then questions can give for the NBT too. Okay, very interesting experiment here, photoelectric effect. You can read your course material and also you can take more information by searching uh, internet, you can take more information, right? Photoelectric effect. Photoelectric effect. Then here, photo means light, right? Photoelectric effect of occurs when light incident on the certain metallic surfaces causes electrons to be emitted from those surfaces, right? The in briefly, I can say about the photoelectric effect. This is the J. Thomson's experiment. The emission of electrons from metals under the effect of light rays, right? Electrons can emitted under the effect of light rays. This is the metal surface can emitted some electrons under the effect of light rays. Photons, light rays, then electrons can emitted. Electrons can emitted photoelectrons. We call this as the photoelectrons. Electrons can emit photoelectrons. We call this as the photoelectrons, right? And some because of the electrons, right? We know current is producing. There is some electrons. It means there is a current. Current in electrons, there is a current. We call this resulting current as photoelectric current. Photoelectric current. Photoelectric current, right? It is more effective, the high frequency of light, right? Okay, then when metal surfaces can remove the electrons, emission of electrons from the metal surfaces under the effect of light rays, called as the uh, photoelectric effect. Then you can see this is the particle nature of uh, electromagnetic radiations, right? We will go back. Okay, right. The emitted electrons are called photoelectrons and they are no different than other electrons. Then name is photoelectrons but same electrons. Okay, we call these as the photoelectrons because under the photoelectric effect, electrons are moving. Then we call the photoelectrons, but they are no different than the other electrons. Right? The name is given because of their ejection from the metal by light in the photoelectric effect. And then you can see one apparatus. Right? And also your book, page number 18, you can see a apparatus. Then here one apparatus. When light is stricken, you can see the plate E. This called this as emitter, right? Photoelectrons are ejected from plate. Then you can see these are the electrons. It's moving from plate E to C. We call this as the collector. Then in this instrument setup, E is the emitter. This is the metal plate. Okay. Then C is the collector. Collection electron can collect here and consists current in the circuit. Then you can see then collector is combined with voltmeter and ammeter. Right? Voltmeter and ammeter you can see. So the light wave is strike the plate E and photoelectrons in red arrow. These are the two photoelectrons. These are moving from E to collector, E to C. Right? When the tube is kept in dark, the ammeter read is 0. If this is the dark, no any readings, no any current. Right? When the plate E is illuminated by light, the light rays coming, having the appropriate wavelength, a current is detected by the ammeter. The ammeter can see motions, moving, ammeter, pointer, moving. Right? The current arises from photoelectrons emitted from the negative plate and collected at the positive plate, right? There is no, keep in dark, no any deflections from the emitter, no any reading in emitter, right? And this is the photoelectric apparatus. Then we can take some conclusions here, right? You can see the photoelectric effect results. These results are useful for our quantum physics development, right? A large voltage, then you can see two lines here. Then if you book page number 19, also there is this one graph. Then in blue line, low intensity and applied voltage and current, and other one is high intensity, right? The current increases with the intensity but reaches the saturation level for large value of delta V. And at voltage equal to more negative than delta V is, the current is zero. This side current is zero, then what happens? Voltage in the negative value. And that point current is zero, right? A large value of delta V, the current reaches the maximum value. At the electrons emitted at E are collected at C. The maximum current increases as the intensity of the incident light increases. When delta V is negative, the current drops. These are the experimental results. When delta V is equal to more negative values, negative than delta Vs, delta V is the minimum value, one mark point, the delta V is equal to more negative, what happened? Then delta V is, the current is zero, right? Delta V is, the current is zero and the delta V is. Some classical prediction and experiment results can explain here. I will summarize one thing, later I will discuss it. Depends of the photoelectron kinetic energy or light intensity. Electron should, then in the classical predictions, then we can say the kinetic energy and light energy. How we explain the classical prediction. Electron should absorb energy continually from the electromagnetic waves. And as the light intensity incident on the metal is increased, the electron should be ejected with more kinetic energy. These are the classical predictions, right? Okay, what is the classical prediction say? They think, according to the classically, we think the light intensity incident on the metal is increased. Increase the light intensity, the electron should be ejected with more kinetic energy. But in the experimental results, we can see maximum kinetic energy is independent of light intensity, right? Then classical predictions say if intensity increase, so electron should be ejected with more kinetic energy. But no, we can't see just like of experimental results. The maximum kinetic energy is independent of light intensity. Okay, if we are increasing or decreasing light intensity, no any changes we can see maximum kinetic energy. And the maximum kinetic energy is proportional to the stopping potential. In this diagram, this is the minus, before the minus value, at the delta Vs, the current is zero. Current is zero. For the more negative values, then delta Vs, at the delta Vs, the current is zero. At that point, we call that as the stopping potential. Stopping potential. At the stopping potential, current is zero. Right. Then in the classical prediction, we think if the metal light intensity is increased, then then electron should be ejected with more kinetic energy. But it is different with the experimental results. We cannot see any changes with the maximum kinetic energy with light intensity, right? Maximum kinetic energy proportional to that delta Vs value. Okay. Then what is the next one? Right? These are very important. You have to explain this, right? The time interval between incident of light and ejection of photoelectrons, right? Then here light incident and ejection electrons, there are some time difference. In the time difference, explain according to the classical predictions. Then what is the explanation in the classical theory? A low light intensity, a measurable time interval should pass between the instant of the light is turned on and the time an electron is ejected from the metal. It means the time interval is required for the electrons to absorb the incident radiation before it acquires before energy to escape the metal. But in uh, experimental results, electrons are emitted almost instantaneously, even at very low light intensity. Right? Electrons ejected instantaneously. We cannot say the time difference, large time difference, I think, and then the explanation in the time interval in classical field. But even at very low light intensity, we can see electrons are emitted instantaneously. Right? Third feature, uh, it is explaining about the dependence of ejection of electrons on light frequency. Right? Explanation about the dependence of ejection of electrons on light frequency. In the classical theory, then in the classical predictions, we can explain it. Electron should be ejected at any frequency as long as the light intensity is high enough. Right? The classical part 1 say electron should be ejected at any frequency because as long as the light intensity is high enough. In the experimental results, we cannot see this type of observations, right? No electrons are emitted. If the incident light falls below some cutoff frequency, there is the cutoff frequency, Fc. At the below this cutoff frequency, we cannot see emissions of electrons, right? If the incident light falls to the metal, but below the cutoff frequency, no electrons are emitted. Okay, in the classical theory say, electron should be ejected, any frequency, but we cannot see at the experimentally, electrons are emitted if the light intensity fall, but no electrons can see below the cutoff frequency. The cutoff frequency is characteristics of the material being illuminated. It is depend on the material character, right? No electrons are ejected below the cutoff frequency regardless of intensity, right? You cannot see electrons below the cutoff frequency. Okay. Then other feature, what is the fourth one? Dependence of photoelectron kinetic energy on light frequency. In the classical predictions, there should be no relationship between the frequency of the light and the electric kinetic energy. Right? Classical ones say there is no relationship between the frequency of the light and the electric kinetic energy. And the kinetic energy should be related to the intensity of light. And the experimental results, the max kinetic energy of the photoelectrons increase with increase in light frequency. Then here say no relationship between frequency and the kinetic energy, but at the experimental results, they say the maximum kinetic energy of the electron increases with increase in light frequency, right? I will give explanation, the summarized explanation later, right? I think you can understand made 4 features in your book. Explanation are here, but summary explanation you can see in the PowerPoint. Photoelectric results, we can explanation and classical prediction, but you can see it is very different with experimental results, right? If yes, in experimental, no. Yeah. If no, experimental, yes. Yeah. So features can see, and we can explain this according to the quantum theory. Yeah. We will explain later. I think we understand what is the feature and what is the classical predictions and experimental results. Yeah. All these experimental results we can explain according to the quantum idea, right? Okay. Then, photoelectric effect feature, we can summarize this. The experimental results contradict all 4 classical predictions. Einstein extended Planck's concept of quantization to electromagnetic waves. All electromagnetic radiation of frequency F from any source can be considered a stream of quantum. Now call this as photon. We know this quanta is as photons. Each photon has energy E and moves at the speed of light in a vacuum equal hf. A photon of incident light gives all its energy to a single electron in the metal. And you have got the idea. One photon equal hf energy of incident light. Light is incident in the metal surface. The one photon gives the equal hf energy. The one photon of incident light gives all its energy to a single electron in the metal. Right? This is important. The single electron. Okay? Right. Then we can build a photoelectric equation. It is very important and you should remember photoelectric equation. We have to solve some questions, right? You can see K max. We call this as the kinetic energy maximum. Kinetic energy maximum we take as the K max. Okay? Or EK max. K max or EK max. In your book it is mentioned as EK. EK, right? Here K max. Then equation is related to the photoelectric effect. Explanation in the experimental results, we take K max equal HF minus psi. We call this as psi, wave function. In wave equation, you can study more about psi. Here, psi is called the work function, the metal. Work function of the metal. This is the photoelectric equation. If you want power cut, please wait. Okay. Please wait.